Hi everyone, welcome to the 24th webinar in 12D's Industry Solutions webinar series. My name is Lisa Stewart and I'm the Marketing and Communications Coordinator here at 12D Solutions. Our Industry Solutions webinars are designed to provide insights into overcoming challenges in an evolving industry in more effective and efficient ways. We'll keep running these webinars regularly and recording them for posting on our YouTube channel with links through our website. Our first 23 webinars from this Industry Solutions series, as well as 22 webinars from our training series, are available online if you missed those. While we wait for everyone to finish joining, I'll pop up some polling questions. You'll have about 30 seconds to answer each, and I'll show the results along the way. Firstly, what design discipline best describes your day-to-day activities? Water modeling, drainage design, roading design, or other? Okay, it looks like we're mostly drainage design people here. Welcome everyone. Next, we'd like to know, have you used 2Flow or other 2D modeling software? Okay, a perfectly even split. I'm sure everyone will get a lot out of today's webinar. And thirdly, what would you primarily use RoadFlow for? Flood and hazard mapping? Secondary drainage flow path determination, road surface ponding and aquaplaning, or other? Okay, quite a mix of attendees here on that front as well. So let's get started. During this live presentation, you'll be able to type your questions along the way, as shown on the screen, and we'll answer as many as possible throughout the webinar. At the end, I'll also read out some of your questions to the presenter if there's time. Today's webinar on RoadFlow will be presented by Dylan Ravel, a Regional Sales Manager for 12DNZ with over 16 years of experience in civil engineering practice, land development, drainage and construction. This webinar will introduce the 12D Model RoadFlow module, which is part of the 3 Waters solutions available to 12D Model users. The RoadFlow application allows users to create, manipulate, and share a 2-dimensional flood model which can be coupled with a 1-dimensional drainage network. The setup, requirements, and procedures of RoadFlow will be shown in a live demonstration during the webinar. Over to you, Dylan.
Thank you, Lisa. Sorry about that. Good afternoon, everybody, and welcome to the 12D Industry Solutions webinar on RoadFlow. I'm going to run through a short PowerPoint before we get onto the live demonstration. And this will just give you an overview of RoadFlow, what it can do, and what we're going to be running through today. Okay, so topics covered in the webinar today. It's going to be an introduction to RoadFlow, setting up 12D model to run RoadFlow, RoadFlow required inputs, reviewing the RoadFlow results, and utilizing these results inside 12D model. So what is RoadFlow? RoadFlow is a 2D quick start. It's the quickest way to get a 2Flow project running from inside 12D model. If you want the determination between the differences between 1D and 2D modeling, you can see our previous Industry Solutions webinar on Drainage 2D, where Rob Graham gives an excellent explanation of the differences between the two. So what does it do? It creates the required 2Flow files from the 12D model elements. It runs 2Flow, it reads the results, it reads the checks files, and accesses the results controller. Who's it for? Well, RoadFlow is an ideal tool for anybody who wants to analyze the behavior and effects of water across a ground surface. This could be for experienced 2D water modelers who require a quick way to set up and review a comprehensive flood model, or it could be the non-traditional model, so use 12D for all the other civil engineering disciplines like drainage and roading and whatnot. What can RoadFlow be used for? It can be used for determination of secondary flow paths, aquaplaning depths, although this is research in progress and isn't a approved solution as yet for large roading projects, flood inundation studies, hazard mapping, and many, many more. And I think you'll find after the end of the demonstration, you'll find your own ways that you can utilize the RoadFlow module. So what does RoadFlow include? It includes an unlimited number of cells for calculation. This, however, is dependent on the base module of the license you currently have for 12D. Constant intensity rainfall on grid, quickest way to get water onto a surface to start seeing the flow paths and how it reacts over the flow. Setting up to 2 Manning's N values or surface type roughness values. ridge and gutter strings for improved grid quality, and flow line position for plot outputs, or what they call PO outputs, and output time interval for high-speed TMO files. So what about 1D models and hydrology? Well, RoadFlow offers integration or coupling with the 12D model dynamic drainage, hydrology and hydraulics package. This operation does require the 12D dynamic drainage and supporting modules, and hopefully this will explain. So the diagram on the right hand side is from our 12D model based module map, and it's included the drainage and services portion of this. So RoadFlow is included in all 12D model 2D drainage modules. The base module determines the maximum RoadFlow cells available. So that's to again determine on your base module license if you've got 100,000 points or 5 million points, and that's the only limitation for the cells, amount of cells in RoadFlow. And the drainage analysis and dynamic drainage modules are needed if you want to couple the 1D network. So those are the three modules on that left-hand side of the tree: the drainage design, the analysis, and the dynamic drainage, and they flow into either the RoadFlow or the 2D drainage modules. There's a red circle there with a VNet. The visualization module allows the rendered results to be viewed and run on a timeline. This isn't strictly necessary for a RoadFlow, but we do highly recommend it, and I think you'll see why. So setting up a 12D model to run RoadFlow, what do you need? Well, you need a 12D model tin or a super tin. You need grid extents to define the model limits, and that's as hard as drawing a rectangle. Other optional data will be explained in the live session. Let's go through the required inputs in a PowerPoint slide, and this will just give you an indication, something to fall back on to live demonstration. The first thing that's required for a RoadFlow is the grid extent, and as I say, it's as hard as drawing a rectangle. This defines a spatial area for the two-flow analysis to be processed, and as a little hint, try to keep it on the tin, because the grid gets the values directly from the tin, so it's always helpful to have some values in that area. The cell size. This defines the size of the cells to be used in the two-flow model, and the cell size that you determine, the time step within the two-flow run will always be half the cell size. There's a bit of give and take with regards to what sort of cell size should I use, and this is really up to you as the designer. Obviously, the larger the cell size, the less calculations that two-flow has to do, and so the faster the run times. The smaller the cell size, the more accurate or the higher the resolution of the drainage model, but it's going to take a lot longer to process. And just as a rule of thumb, if you halve the cell size, it's going to take up to 8 times longer, or it needs to do 8 times more processing when you halve the cell size. The Manning's N, this is the default Manning's N, or the surface roughness, to be put into the two-flow 2D run, and this is to help determine flows and velocities over the surface. The rainfall, this is used for a constant rainfall on grid analysis. As I say, it's one of the quickest ways to get rain or water into the cells, and this can be run individually on its own, but if you are linking it up with the 1D drainage network and using the hydrology from that, then that can actually be changed to 0, and all of the flows will be totally determined on the 1D network. The duration, this sets the time for the duration of the analysis. And conversely, the output time increment, it sets the incremental time for the writing of high-speed TMO or results files. It's like a little snapshot of the model at that stage where we can view in 12D. The mapping depth cutoff. This sets the minimum flow depth for cells to be included in the results models. When you do a rain on grid in particular, you'll have rain falling on absolutely everything, and you may have cells which have very, very shallow flows which really don't impact or affect your model itself. So you can put this mapping depth cutoff. So in this example, it's not going to show any results less than 150 millimeters in depth. The ground tin, this is the 12D model constant that you have to do, a tin or a super tin, and this calculates the cell heights for them for the two-flow grid. The new two-flow grid tin model, this is the 12D model grid tin that will be created with the grid elevations. And the folder is a user input, and this is the folder that creates and updates and stores all of the files from the 2D run. Now, if you want to save all of those results from that particular run and you want to do a further analysis, it's as simple as changing the folder name, and 12D will create a new folder with all of the results and the logs and the runs from that second run or that third run, and you can recall those at any time. And the format is the file type for the spatial files that will be created as part of the two-flow run. These can be a mid-MIF or a shapefile format. Right, let's get into the live demonstration, and we'll run through run through RoadFlow and its procedures. Before we start, there's two inputs that you need to put into the RoadFlow which come directly from 12D model. These are the grid extents, or the spatial area where you want the run to be assigned, and also the tin. Now, when it comes to tins and modelling surface obstructions, like buildings, for example, traditional modelers, they will manipulate the cell heights to account for these obstructions in buildings, but 12D users, they like to see what they're going to get with the levels, and they typically put all of those obstructions and model them as part of the tin itself. I'm just going to run through a very quick and very old macro, which is very handy, especially for 2D modeling and forming obstructions, especially around buildings. And this is activated by the tins user create buildings for tin. And I'll just find where that panel's popped off to. There it is. Okay, the great buildings for tins. And this just takes a data source. So it takes a source of 2D polygons. This can be from what we've got here, which is survey data, or it can be simply from polygons that are generated from a GIS mapping application for where the buildings are. I'm going to create these building models from the 12D model survey building. And it'll create two models, a building floor and roof model, and a floor only model, which can be used for including into your tin for your nulling and setting includes and excludes. The ground tin is the levels that it's going to drape the floor level onto, and the building height is just a constant building height that'll put in through the model. And you've got colours for roof colour and colours for wall colour. And if I process that and then turn on those models in the plan view, the building floor and roof, you'll see it's basically replicated right over the top of the existing polygons to some new string models. And if I do the same thing in the 3D view, you can see that it's created building floors and building roofs that can be used to create a tin and add it in as an obstructions model. So I'm just going to quickly create a tin of all of that model. I'm going to call this tin building. And I'm going to give it a color purely for visualization purposes. And the data that this is going to be created from is the building model. And it's going to create triangulations all within those separate polygons. So what I'm going to do is I'm going to apply nulling, a very small value, that's going to get rid of all of the triangles that are formed between the buildings. So if I triangulate that and finish, I'm then going to add that to my super tin, which is going to provide the basis for the cell levels for my 2D analysis. So I'm just going to edit the super tin, and my super tin is called 2D analysis, and I'm going to add that building tin to the super tin. And you can see now the combination of both the ground levels and obstructions are above ground building obstructions. Very simple and easy process that is very easy to do inside 12D. Okay, getting onto the RoadFlow, I'm going to activate the RoadFlow from the Drainage 2D menu. And we've gone through the required data, so I'm just going to fill that data in. So first off, we need a two-flow grid extent, and this is going to be a rectangle that's drawn. It can be a rotated rectangle, as I've got in my example here, and that will create the cell orientation based on those rectangles' four sides. The cell size, I'm going to put in a cell size of 4, purely for the reason that for this webinar, I know a cell size of 4, though over that area, it's going to take about 30 or 40 seconds to run. Now, if you're unsure how many cells it's going to produce, when you put it in the cell size and hit enter, 12D will actually calculate and tell you how many two-flow cells it's going to create within that region. My default Manning's N value is going to be 0.035. And I'm going to start off, our first example is just going to be a constant rainfall on grid. So it's going to constantly rain on every grid and with an intensity of 100 millimeters per hour. I'd like the run to go for 0.5 hours. And these snapshot high-speed TMO files, I'd like to see the results every 30 seconds. The mapping depth cutoff, I'm not interested in any of the results that are under 20 millimeters deep of water depth through my cells. And the grid tin, or the tin model it's going to get its height from, is my super tin 2D analysis. And the new two-flow grid tin model, I'll call this RoadFlow. And I'm going to do the same thing with my folder. I'm going to call that folder RoadFlow. And it's going to store all of the results and the time steps from within there. And so that's the required data. That's all you need to fill in to run a RoadFlow. But what I'm going to do is I'm going to add in some more models from the optional data tab, which is going to further refine or condition my model and help set the levels of the cells. So I have a view here called 2D strings. And this is where I can explain these strings and what they do. First of all, the boundary crest tolerance. This is all about boundary conditions. If I didn't put a boundary crest tolerance in, it's going to have one boundary condition for each of the four sides of the rectangle. But where I've got defined channels coming in and out of those grid extents, what I'd like to do is have separate boundary conditions from those. And so I can put in a boundary crest tolerance or a minimum channel depth, and 12D will split up those into separate boundary conditions. The drainage model I'll do when we go and couple it with a 1D network, but we've got this thing which is the geometry modifiers, and you have two there. There's a ridges model and a gutters model. And the ridges model are all the strings that are contained within one 12D model. You can have many strings in there, and what they're going to do is define the high points, or they're going to raise the cell levels up to the levels of that string. And so I've got a defined string here, which is the crown of my road, which will provide the weir, or the top of the weir. So I'm going to specify the strings in that model as my ridges model. And then conversely, for the gutters model, if I want to lower the cells to a particular Z value from a string, I've got all of my defined channels, or it might be your inverted curves if you're just running this on an intersection, and you can define all of the strings within that particular model as your gutters model. With the RoadFlow, you can set up to 2 surface roughness types, or 2 Manning's N values. The first one is put in the required data tab, and then you can have a second one in the optional data for the material roughness. Now, what we can delineate within 12D is all of the polygons in the model. I've got some polygons in a model here that's going to determine where my different roughness values are. And because they're mostly hardstand, I'm going to put a Manning's N of 0.015, and I'm going to choose that model as the model of material polygons. And finally, we have this flow line graph model. When we get the results from 2Flow, we get results for depth and height and velocity and hazard. But when it talks about how much water is actually flowing through a cell, or what's the quantum or the Q, we need to specify plot output points for the 2Flow engine. And we do this in 12D lines or strings in a model. So I have a model of strings here where I've defined where I would like to actually get results or plot output results for the flow that's running through those cells. And we do this by drawing a string, and the only rule is you draw it left bank to right bank so it's facing in the direction of the flow. And there can be as many strings in this model as you like, and I'm going to set that model as the flow line graph model. Okay, we've got everything that we need to go away and do a RoadFlow analysis, so I'm just going to hit run on that. And you'll see that 12D will pop up a little graph, and it's going to give you values about the run on the left-hand side, and it's going to give you those graph values on the right-hand side. And if you notice up the very top left, the number of wet cells is not changing for this particular run. There's over 9,000. And that's because we're doing a rainfall intensity on grids. So there's water impacting on every single one of the grids within the defined area. So essentially every cell is going to be wet. Okay, so that's just about done. That's done now for our 4-meter cell size. And we'll go and have a look at the results that it takes. But before we do go and have a look at the results themselves, let's have a look at what it's actually done to these strings within this model, because there's a rule in 12D for when you're talking about these strings that are going to change the way that a 2D model works, and that rule is one model, one purpose. So all of the strings in those models have to have that particular purpose for the 2D drainage. Like, you won't want to go putting any center lines or super alignments or anything like that inside your flow line model, for example, because that'll just make the model unstable. So it's one model, one purpose. And as soon as we activated that 2D drainage run, it's assigned some attributes to those strings. And the attributes for 12D superstrings is the way that we pass the data or the correct codes or the commands across to the 2D network or the 2Flow engine. So if I first have a look at these flow line models, it's assigned a code of Q for all of the strings within this model. The name is from the name of the string that I've put on the superstrings, and it gives you a comment which is a bit of an idea of how that's interacting with the 2D engine. If I look at the gutters, all of the strings in the gutters have been assigned appropriate attributes, and this attribute has actually got a group with a Z from string, and that turns that on with an integer value of 1. And lastly, the attributes that have been assigned to the materials model, it's just a single one with a type with an integer of 2. Now, what does the integer of 2 mean? When we ran the RoadFlow and typed in a folder, 12D has created a whole separate folder with the same name of what you've typed in. And it's contained all of the subfolders and all of the files that need or have been created to make that analysis run. And inside it's created a CSV file called materials and roughness. And if I open that CSV file that's been automatically created, you'll see there is 2 roughness types within the CSV file. Number 1, which was our default value we put in the required data, and number 2, which was our optional value. And this is where the number 2 comes into play, where it's telling the engine to come and grab this value from roughness value number 2 inside the CSV file. Okay, so it's assigned a lot of attributes to those strings. Now let's go and have a look at some of the check files that it's in, or the graphical representation, so you can see what's running in behind in the 2D model. First thing I'm going to do was, before I read the results, I'm going to tick on this read Z points check file. What this does is it reads in a grid tin with the exact levels that have been passed across to the 2D drainage model. So essentially, you get to see what 2Flow sees when it's doing its run. And the best way to demonstrate this is, I'm going to flick on that 2D view, and I'll just go to a position. And if I read the results, I'm going to turn on a model. It's a check file called ZPointCheck, and that will turn on the actual grid tin that was created. So you can see, based on that cell size, exactly what levels have been passed across into the 2Flow model. So what you see is what 2Flow sees, and you can see how, depending on the cell size, it hasn't exactly picked up those obstructions or those buildings because it's only sampling at that size. And if I turn off the tin itself and redraw that view, this is exactly the levels that 2Flow has been running. So that's a really good graphical indication of, hey, you've got lumps and bumps, and hey, why is the water stopping here? It's because the level that's been assigned based on the cell. So I'm going to remove that model, the check model, and I'm going to turn on the tin model back on because we're going to need that later on in the day. Okay, so that's the first of the check models. It creates a whole list of models with the word CHK in them. I'll just move that across to the right-hand side. Make that a little bit easier to see. And we'll start turning on some models. First of all, we're going to have a look at the boundary conditions. These ones don't actually have a check model prefix, but there's an exterior BC, which is created when you first run the RoadFlow. And if I turn on the gutters model as well, you can see when we put in that boundary crest tolerance, what it's actually done and passed across to the 2D engine. Each one of these strings has a boundary condition assigned to it. And you can see, based on the different colors from that boundary crest tolerance, where it's actually split the line and assigned an individual boundary condition to each of those little segments of string. And if you want to know what those are, you can actually just go in and have a look at the attributes of that file, and you can see that that's set that as an HQ boundary, which in 2Flow language means it's the depth of flow exiting or entering the cell area is totally determined on the depth of flow, which is in the cell itself. There's also another model that helps explain what the boundary conditions have been set, and that's the BCC check. And this gives you individual superstrings where the boundary conditions have been set on the grid cells. And again, you can have a look at the attributes of these. And it gives you what the attribute type is, and it gives you a little bit of information about where the source comes from. And so this is just set a individual or a constant boundary condition, which is a slope of 0.2 meters per meter. Okay, next on the check files, if we have a look at the domain check, you can only have one domain or one 2D domain within a RoadFlow model, and that should closely coincide with your grid extents. Well, it should be right on top of your grid extents based on the models, and that has attributes within itself. When it comes to the points and the gutters and the strings and those models in here, the geometry modifiers that we put in, it's created a couple of check files with a Z object check and a Z point check. If I turn those on, and you'll see they're right over the top of the gutters model. And this is just to be able to get a graphical representation of what's been going on and what sort of data is being passed across to the model. If I zoom in a little bit closer, you'll see it's got a little indicator there with an upside down triangle, and that indicates that it's a gutter model, and that Z level has been lowered, or the cell Z level has been lowered to match the Z level of that 12D superstring. If I toggle on the Z values, that's currently got a Z value of 29.95, and if I do a string inquire on the original 12D superstring, that Z value should be pretty much exactly the same or very close to the Z value that it's assigned the cell. Now, these don't exactly line up because it's very unlikely that the sides of the cells will actually line up exactly with the 12D string. As I say, very unlikely, but it gives you an indicator of what's been happening under those 4 meter spacing cells. And the last check model we're going to look at is the messages. Oh, sorry, the PO check, the second to last. These PO checks are obviously where we plot in our plot output points, and they should very closely match the output points that we specified from our 12D superstrings. And they have attributes within themselves, which is got a Q attribute command on it. So that's a plot out point for flow. Now the messages. We create a check model for messages about things that's happening when you're running the model. Now they come into as a superstring, and that superstring has a name and has a bit of text, and it just gives you a bit of information about what's going on, why the model might be have instability in that area. And you'll see that it's actually got a very descriptive string name, which is the name of what the actual comment is. A really handy way of getting around these and checking these is via the use of the string info table. So if I fire up the 12D string info table and look at that messages check model, you can see quite clearly that the string names are all those check messages. And if you want to navigate through those, you can simply just select that and navigate through them on the string info panel, and 12D will automatically pan your plan view to where those messages are in the location that they are, and it'll give you a really good idea of whether those are going to make a difference to your model or not. Okay, so we're reading 4 check models. And when it comes to the results and viewing the results, we create 4 tins or grid tins. Now these are like tins in 12D, they're just tins that can change the Z values. And if I go to the plus button and type in the results, we have 4 tins. We've got a RoadFlow results, results depth, results hazard, and results velocity. And we'll have a look at those different values. But for now, and the one that I'm going to manipulate in the results controller is just the base one called RoadFlow results. So if I turn that on into this view, which has the tins contours toggled on, you can see that in plan view with the tin contours. And if I activate the 3D view and just arrange that over to the left side and turn on that same model, you'll see it looks a little bit different in an OpenGL view. It's actually got a rendered rendering or a height rendering on the tin, and we'll show you how to manipulate that too. Okay, so we've got 4 tins that are created. And if I want to manipulate those and see different things, I can go into the results controls directly from the RoadFlow panel. And I'm currently going to be manipulating this grid tin that I have turned on in the view called RoadFlow results. On the time step, you can see that we've got 61 time steps because I set it to going for a half-an-hour run at 30-second intervals. So we have 60 results there that we can view. Now the tin inquire result for this particular grid tin is currently set to the result water level, which is why the tin in 3D is showing the water levels itself. But the tin display result, when I toggle on the contours, it's actually showing me the contours as the depth values. And just because it's a tin, you can do anything that you like in 12D that you can do with the tin. You can go into the tin settings, you can change the increment that you're seeing those results in, you can change the colors that they're showing in. It's essentially, for all intents and purposes, a 12D tin. Now, what does it mean by the tin inquire result and the tin display result? Well, the inquire result is what the actual values are. So if I go and use the tins inquire, tins on a view, when I move my mouse over a view that has that tin turned on, you can see the actual height, or the Z value of those tins themselves are the water level, even though the contours that I'm seeing, the display result, is the depths. And at the risk of making a great big screen full of mess, I'm going to go on and I'm going to turn on all of those other 3 results tins. There's a depth, a hazard, and a velocity. So you can see what values these have been adopted by. So when I now move my mouse around on the tins on a view over the details, you can see what the values are for the results, the depth, the hazard, and the velocity all in one go in any particular area which is coincidental with my mouse. Okay, I'll turn those off because it looks a lot of mess because you're seeing the contours for both depth, velocity, and hazards, and we'll go back to just using the RoadFlow results itself. Now, this rendering, if I just go into a position here, if I look at the culvert outlet, you can see there's a different colouring. Now, this is a tin height rendering. And all it does is it uses a bitmap swatch to basically distribute those values over the tin. And if I go into view visualization tin height render settings, this is where you can change the values in those bitmap coloring. Before I get a minimum and maximum height, I'm actually going to see what, for my particular project, the minimum and the maximum height are on the tin. And I'm going to do that by tin info. If I look at the results depth, it's telling me for the depth I have a minimum depth of 0 and a maximum depth of about 3.3. So when I do my height colouring, I'm going to apply the settings on this results tin using this depth bands. Now we ship some for you. If I open that up, you should see quite easily what the actual depth banding is for. It's just a bitmap swatch that's going to be distributed over those height ranges that we specify. And we give you a number of those loaded with 12D under the library folder under the drainage 2D. So you can have those to start with, or I'll show you later on how you can make your own. I'm going to set the minimum height of 0 and the maximum height of 3.5. If I set that and redraw that 3D view, you'll see that it's distributed that color banding over a different range, and I've got a few more color bands there inside the actual view. Okay, some of the other results. If I change this tin inquire result from water level, we can change it to whatever we like. So this grid tin can take other values so that we can color it and do other different things with it. I'm just going to run it by a result velocity vector and go set. And so what you'll see now is the contours at velocities in meters per second. And if I zoom right in, you'll also see we've got some velocity arrows or flow direction arrows, and they are currently at an arrow scale of 1. So 1 meter on the actual, or 1 unit inside 12D equates to 1 meter per second. And just to check on that, if I go back to the tin inquire, tins on a view, on this particular one here, we've got a velocity result of about 0.77 meters per second. And if I use the 12D measure tool and measure roughly between those 2 points, the value on that should be pretty close to what the actual value on that tin arrow scale is. So if you want to see those a little bit better, you can actually manipulate the scale of those. If I change it to an arrow scale of 2, then when I measure 2 units on the screen, that's going to be 1 meter per second in velocity. And what we can do with any of these tins is we can step through the time steps. I'm just going to zoom into where we've got a swale outlet. If I go to time step number 1, this is where it just starts raining, and step up through there, we're going to get some velocities start to happen. And it's going to be running down the swale, and there's going to be very, very small arrows because there's going to be no velocities where it's ponding up behind this weir. But what's going to happen over time is it's going to fill up behind that weir swale, and it's going to start spilling over and flowing off into other places over the grid. And it's going to be running faster because it's going downhill. So you can manipulate those to see whatever you like. If I change that back to result water level and go back, say, to time step 10, as I step up, you'll see in 3D that water getting higher and higher and higher. Now, you'll notice that right behind that culvert, we're getting quite a depth of water. That's because at the moment, RoadFlow has absolutely no idea that there's a culvert running underneath the road. We haven't coupled it with our 1D network, so all the water can do is head up behind the culvert embankment and get deeper and deeper and deeper until it gets to a stage where it runs over the road, which in this particular case it doesn't with the length of time that we run. So that's a lot of visual feedback that would be familiar to 12D users, manipulating tins. But when it comes to reporting or outputting, with the 2D drainage, you want to do it in different ways. So what we can do inside 12D, if I just change that to maybe the last time step so we're getting our maximums there, we have the ability to graph the results. And so from the drainage 2D menu, I'm just going to select 2Flow results graph. And you can choose exactly which one of those results tins or values you want to graph. So I'm going to go to the results depth, and I'm going to create a first legend or a first position called culvert inlet. And I'm going to spatially pick on a 12D view where I would like that results graph to be populated from. And that's populated that position, and it's giving me a dynamic time series graph, so we're getting a depth over time. And you can have as many of those on the same graph as you like. If I create another one called swale outlet, and I'd like that swale outlet reported at the maximum depth in that position there, you'll see that it's automatically created a different legend for each of those positions. And like any time series graph in 12D, you can manipulate it. You can change the way it looks just simply by right-clicking on the graph. You can change the color, the border styles, the font size. I'm getting a little older, so I'm going to change the font size to large. You can change the plotting method. You can either have it as a line or a bar or a point. There's many different ways that you can represent that graphical results. And you can customize your own things, and you can mark the data points. But what's the most important is being able to get something out. That looks great in 12D, but you can actually export that graph dialog to a number of image type files. So you can copy and paste those or save those into a report file. And you can also output some text. So if you want a map or graph in your own particular way, you're just wanting those results out in a text file. I'm just going to create a file here called results.txt will be fine on my desktop. And if I export all of those settings and then go and have a look quickly at that file on the desktop, you'll see we're getting each of those positions with the names that I've put in, the time step, the time or the delta time, and what the actual value is. In this case, the value is the depth. So you can output very easily and quickly and map that or graph that however you like, whether you want to copy and paste that into Excel or even just share that results data with somebody else. Okay, another way of getting that data out is we've got these wonderful tin height colors, but when you plot that out on a plan, it doesn't actually mean very much. So what's really handy is to have some sort of an indication or some sort of way of graphically showing what that colorization means. And we've got a way to actually tabulate a legend from the tin height values. So I'm going to tabulate that results. I'm going to create my very own bitmap, and I'm going to create it from a range file. So I'm going to put a new file name in for the render file, and I'm going to create it based on a 12D range file, a simple height range file called depth default. And if I open up that height range file, it's just a familiar thing for 12D users where you can customize and make your own height ranges. But the difference is those numbers are irrelevant when it comes to a height range file. So from the legend model, I'm going to create a legend called TUF legend. I'm going to give it a variable height, and I'm going to put it down here on the screen. The title will be depth results. The scale is going to be depth, and this is where I can set my minimum and maximums, and my increment I might go 0.25. Now, before I hit run on this, I'm actually going to change the text style because it takes the current set text style in the CAD properties toolbar. And if I go create and turn on that new model, we have an automatic legend creator from those results. But what it's actually done is it's applied that brand new bitmap swatch to that tin that it was applied to. So it's a very quick and easy way of creating your own height render files or height render settings. So that's if you've got the visualization module. You can see those tins and you can see them with the height rendering. If you don't, and you're using the limited cell RoadFlow within 12D, that's okay. There's the other ways, but there's also some very handy ways to manipulate that and get that onto a plan. Because these are tins. If I would like to export those colors to plots somewhere else, what we can do is we can simply just run a contouring and labeling. So from a layout file, I'm just going to bring in a contours and labeling function, and I'm going to contour and label, in this case, the depth results grid tin, and I'm going to create a contour model for contours called TUF depth cont. What I'm going to do is, rather than take the base color cyan for this increment, I'm going to use a range, and I'm going to specify using that exact same height range file for my ranges for my depths, and I'm going to interpolate the colors. So if I hit process and turn on that new model of contours, you'll see that it's actually created contour elements with that same height range. And for plotting purposes out of 12D, you want to make it look kind of nice, and they're just super strings. So I'm just going to quickly go into super strings. I'm going to add a fill to those super strings. So everything in that depth cont, I'm going to set a solid fill on it using the string color, and I want it semi-transparent, so I'm going to make a blending of 0.5. And if I change that, you'll see that's now got a nice solid color. So for your flood and inundation maps, or really just graphically showing what you're getting from those results, that's a really quick and easy way to do it. And just for plotting, I'm going to be a little bit anal, and I'm going to turn on the raster in the background. So you can imagine what that would look like, plotted to a PDF out of 12D. It's very nice and easy. So those are graphical mapping and ways that you can actually use the results files from the 2Flow run. But what about the 1D? We've got all this water ponding up behind the culvert. So I'm going to do another run, but this time I'm going to include my drainage in it. Now, before you even think about joining or coupling a drainage network into a 2D network, you've got to make sure that all the settings are correct in the drainage network itself. So I've got a view here which has got my simple drainage network, and it's all up and ready to go. So I'm going to just go and open my drainage network editor and load that network up. And of course, there's three ways that you can get flow into drainage or a drainage network inside 12D. You can obviously type in a catchment area, or you can have a catchment polygon, or you can simply have a user-defined inflow hydrograph. And we've got a couple of those. If I go to this point here, I have a catchment area from set number 1 of some 0.04 hectares. On the swale inlet, I have a catchment polygon that's been set for set number 2, which has a slightly larger one. And right up the top here, I've got an item in 12D which was called a bypass pit. So it's a pit that has no inlet capacities. And even if you're not looking about doing catchment areas or the hydrology from the 1D network, if you simply want to enter in your own user-defined inflow, this is probably the quickest way to get a hydrograph into your drainage network. You can simply have a node or a bypass pit that you can enter information from. Up in 6 it is. I actually have from set number 3 a catchment area set to it, but if I wanted to put in my own user-defined inflow in a dynamic network, you can do that under the pit inflow tab, where you can put in your own flow over time, and that will be used to pass into the 1D, which will then be used to pass into the 2D network. Now, you do have to be doing a dynamic analysis to couple it to the 2D. But if you've only done a rational analysis to get your peak flows, there's a really great little tool to be able to get those peak flow results and put them into a dynamic network. And that's under your drainage sewer create. There's this item here called create hydrographs from peaks. And what you do is you specify a drainage model that's had a rational run done on it, and it will actually create a triangular peak flow and put that in this corresponding pit inflow tab for you. So I encourage you to give that a go. Okay, so under the hydrology that I'm using for these catchments, I'm going to use a ILSAX2 method, and the hydro file I'm using is just one of the example ones for Brisbane that we load with 12D. The only difference being is under the temporal patterns, I'm only going to be using one, purely for the time. If I wanted to run 3 or 4 different storm or 3 or 4 different temporal patterns, I can absolutely do that. And 12D will create TMO or 2D files for each of those as it runs. But just for this exercise, I'm only going to do one. So before I couple that to a 2D, I want to make sure everything's running nicely. And so I'm just going to go and run that drainage network as you would do, and probably a lot of you have already done. And we want to now go and put that into the overland flow or the drainage network. So I'll go back to the editor and just close that drainage network edit panel, and we'll come back and have a look at the flows in a moment. Okay, running a road flow coupled with a 1D drainage network. I'm just going to do that via a layout input because I don't want to have to fill everything out again. Now, looking at time, we're going pretty well at time at the moment. So I want to do a cell size of 2. Now the cell size of 2, I previously did one with a 4 meter cell size. Doesn't mean that it's actually going to take 8 times as long to run, purely for the fact is we're not going to be doing any rainfall on grid. I've set that to 0 millimeters per hour. So the number of cells that are actually within the run are only going to be the ones that are affected by the 1D hydrology. So it doesn't have to do massive amounts of calculations on every single cell. Everything else is pretty much the same as what we had before, but I want to store these results in their own folder called 1D because I want to keep the road flow ones there and pull off those results later on if I want to. So I've just changed the folder name. And the only other thing that I've done over and above what we did initially is I've specified a drainage model. So that drainage model is going to be specified and run. And if I go ahead and run, this is going to take about 2 minutes, as opposed to the 40 seconds at the 4 meter cell size. Now you notice up the top, whereas before I think it was something like 9,000 wet cells, now that we're not doing a rain on grid, these number of wet cells is actually varying, and it's a lot less than the 9,000 we had when we did a rain on grid. So it will be, if I did the same 4 meter cell size, it would probably be a lot faster to do the run than the initial one that we did. Now at any time, if you want to start a run and just see that things are working, you can actually select finish anytime that you like, anytime during the run, and 12D will store all of the results that have been created up into that time step. So if you're going to be running a 2-hour analysis, and you get sort of 2 minutes in and you see something becoming unstable in the analysis, you don't actually have to wait for it to stop. You can just hit finish and then go ahead, read the results files and the check files up into that point and see what was going on and see where the errors are. Okay, so that's about 50% of the way through. Yep, so we're going to take about 2 minutes. So maybe a good time to think about your questions for later, guys, because we're almost done. And I might actually, I won't finish that one. But I guess a lot of time with the 2D analysis, because it is doing an enormous amount of calculations, you've got to have a bit of patience. But before that finishes, if you're running a standalone 12D dongle, what you can actually do is you can open another 12D model project and read in the results from the run that is currently going, so you can check and see how it's running as it goes. And you'll see when we look at the results controller, you'll see there's a thing called monitor results, a tick button, which will monitor the results that is running in another 12D project. And so you can see how things are going and start analysing those results even before the run is finished. Another good tip. But if you want to open 2 instances, you obviously need a standalone dongle. Okay, that's done. So what I'm going to go through here is I'm going to go and read those results. I'm going to click on the yellow folder, and you'll see the log file. There is only one log file, so it's taken that folder name, it's taken the drainage model name, and what temporal pattern we were running. So if I was running 3 or 4 different temporal patterns, there would be a log file for design 60 and design 30 and design 25 that you could read the results for. I've only got one, so I'm going to read in that stormwater design 60, and I'm going to actually put the prefix a little bit shorter. I'm not going to worry about reading a Z-points check file because it's going to be slightly different. But if I go to read results, that's read in all of those check models and the results models as per what we had before. If I go into the 2D results, I'm going to turn off the previous results and turn on results 1D SW design, because I took out the prefix for results. And if I turn off those previous contours that we created, the 2 flow depth contours, you can see there's a lot less ponding in behind that culvert that was happening before. And to see that in 3D, turn off that previous results, turn on the 1D SW design, and we have a look at the information on that tin. So if we go tin info and look at the 1D depth, it's now only a maximum depth of 2.3. So I'm going to go and change that tin height render settings like I did before, but this time on the 1D design, and change it to say 2.5. Okay, so we get those results in there. Okay, so now what we've got going on is we've got the flow approaching the culvert, the 1D network taking over and flowing that out. To see that in action, if I go to the results controller and go to time step number 1 out of 480 and go set, this is where it just starts flowing. Actually, I'll change it to a position looking downstream and start running these through, and you'll see what's happening is the results coming from those catchment flows are starting to flow down that channel, and we've got a much higher resolution. We've got a 2 meter resolution grid, so they're not quite as coarse. Then if we go back to the culvert outlet, we'll see that the water that actually flows into the culvert flows out of the culvert. Okay, so it's actually coupled in with that 1D drainage network. And then you can use all of the results and manipulate them and change them as we did with the first RoadFlow. There is one extra thing that I'm going to check is, hey, is the water that's supposed to be coming from the catchment flows into the culvert the same as what's going out? And I'm going to check that via 2 things. First, the 1D and then the 2D. So we've got these plot output points where I've asked for flows. And I've got one just downstream called culvert outlet. And so if I go to the graph, plot output results, and ask for a plot out result at the culvert outlet, and we now have a new folder called 1D. Okay, we've got a flow coming out over that 2D cell of about 7 cubic meters per second. How does that compare to the actual drainage itself? If I go back to our drainage design and load up that network and look at that particular culvert pipe, look at the results flow for the pipe graph type. It's popped up on the other screen. You'll see a very, very similar flow that's coming through or approaching the culvert, going through the culvert pipe to what is just downstream of the culvert. So that's always a good little check there between the 1D and the 2D. And the last thing I'm going to do is just show you a little bit of the visualization, because once you've got the visualization module, you can do lots of cool things. You can put trees and plants and roads and houses, you know. So your output for your people or affected parties by flooding, you know, you can create a nice little video of them. And we do that via a timeline. And I'm just going to show you a very quick timeline. We give you ones installed with 12D, but I've got one here that's already primarily set up. And so this is a simple little timeline. It's just a floating eye and camera. We give it an eye position, we give it a target position, which is basically right in the middle of the road. And then we've got this item on the timeline called a two-flow warp. And if I look at the settings for that, we've got it typed as a two-flow warp. You've got a start time and end time, and you've got this thing called a modifier. Because we ran a 60-minute storm, we don't want to wait 60 minutes for that to finish. So we have this thing called a modifier or a warp, which will basically multiply that by 100 times. So if you're running a 24-hour storm, you don't have to sit there and watch it 24 hours to see what's going on. And then with regards to the two-flow water heights, you just choose your particular event or your results. And if I run that, I'll just get that out of the way. That's going to be running that two-flow event, and you'll see the water start to approach the culvert. The depths get a little bit bigger, and then the water flowing out of the culvert. So it's a really nice, quick and easy way to, as I say, for affected parties or project partners, you can create a video from that, from the timeline. And then if you've got a little bit more time on your hands, rather than to just do the modeling, because you've got all the capabilities of the visualization module, I'll show you one that Rob Graham's done, which is absolutely fantastic, and you've probably seen it before. You can go a little bit more effort, you know, put in your roads and your visualization and your fences, and what you'll see here is it's actually running a two-flow results tin on a visualization as basically it's walking down the road. So that's always something that's nice and handy, that comes as a bit of a bonus for the visualization module when you're running it with your 2D drainage as well. Okay, thank you, that's me. I'll pass you back to Lisa and we'll see whether we've got any questions.
Thanks for that, Dylan. We've had a few questions through. Because of time, I'm just going to read out two of them for now and
Sure.
get back to everyone else by email later. Emily in New South Wales has asked, is it possible to view a long section of a pipe run?
Long section of a pipe run? Well, actually, that's a really good question. Yes and no. If I go back in and I show that long section of that culvert, the hydraulic grade line, or the depth of flow within the culvert, is purely from the dynamic drainage itself. But if I turn on that results tin, you'll see that's the actual two-dimensional depth results from there. And so for a long section, I'll just pull up the results controller. And whilst you won't see anything happen within the pipe, you'll see it happen upstream or downstream. Or thinking, if you want to create a plot of the depth of water within inside a section, you just do normal 12D procedure. If I go into design and I go to time step number 20 at the stage, set, you'll see that that's the height of the water upstream and downstream of the culvert at time step 20. And as you click up, we'll get to the point where we're getting our maximum values, and you'll see that will coincide with the maximum water level when passed across to the 1D network. So hopefully that answers your question, Emily.
Great. And Adam in Brisbane has asked, how does RoadFlow connect to the drainage pits?
Oh, that's a good question as well. I kind of skipped past that, but if I go back into the drainage network editor, as soon as I connected that through and I specified that drainage network, what 12D's done further on to the network editor is, under the global, it's basically enabled the two-flow and two-flow temporal pattern there, and how it exactly connects with the pits itself, 12D takes a bit of a guess or a educated assumption, shall we say, at the start. depends on what the inlet data or the KU method is. I've got a KU method of culvert inlet set here, and so what 12D is done and set to 2Flow is that the 2D connection type is a sump. It's going to lower the cell to the sump level of that pipe. Whereas if I went to a number 1, which is a grate or a sump, it's actually made an assumption based on the KU method that that is a grate connection. But if it gets it wrong in its assumptions, you can always change those. And that's how it interacts with the cell coincidental with that 1D drainage.
Wonderful. Thanks, Dylan, and thanks to the audience for your great questions. As I mentioned, we'll get back to the others individually by email. The recording of this webinar will be available in coming days through our website and our YouTube channel. Our next Industry Solutions webinar will be a special presentation by 12D Synergy partner Abtrack on the 17th of May. We've also got some great training topics coming up, so keep an eye on our emails and social media channels. If you need to contact us in the meantime, our details are on the screen now. That concludes our presentation for today. Thank you everyone for attending, and we hope to see you at future webinars.